You know about this. Now regarding exam 1, I have an offer to make. But we can operate on this offer only if everybody is of a mind to be happy with it. The offer is this. If you wish, and this is something I prefer, instead of having the exam Thursday evening, I'll give you the exam Sunday afternoon. 4 hours, if you want it. 1 p.m. to 5 p.m. Or if that doesn't work, 2 p.m. to 6 p.m. That's a lot more time. And if you opt for this, you'll get the same exam that I would give Thursday, which means multiple choice format, but now I'll throw in some additional questions, which as students refer to them are white space or free response, because those are the real types of questions that you should deal with. Unfortunately, in the long term, that means fall or spring, I have not the time nor wherewithal to give you the best kind of exam, which is strictly free response. It's just too much. So I will offer you a mixed bag of multiple choice and free response, which parallels the quizzes, if you are of a mind to accept my offer. Now, this offer can only materialize if everybody is satisfied with it. I'm not in a position to twist your arm or force your hand, because I know damn well that if as few of you as one goes to the administration of this university and says, Horvath made me take the exam on Sunday and I object, the administration is going to come after me. Anybody not happy with this? Good enough, we'll stick with Thursday. I think you can find the location, because you are presently sitting in such. Now, just to remind you, when you assemble for the exam, which will be Thursday evening, I want you to sit as far apart from each other as you can. We got enough room for everybody to be spaced so that nobody needs to have a nearest neighbor sitting in the adjacent seat. That's no problem. I'm sure you know how to wrestle with this. And even though the university time frame for assembly exams terminates at 10:10, I'll let you work till 11 o'clock. Because you're here Thursday evening anyway. So why not take some extra time? Because I don't want you to operate under time constraints. I want to find out what you know. Now, I can't do that very well with multiple choice. That's why the free response exam, one more reason thereof, is much better. Nor can you get part credit on multiple choice. Another reason why the free response exams are much better. And for me as a faculty member to have to sit down and waste time inventing bogus answers so I can create a multiple choice format test is pretty damn stupid. But unfortunately, as I said, I don't have the power, nor energy, nor time available to operate in any other fashion during fall or spring. But summertime, I give strictly real exams for your information. In any case, more information on the exam as I develop it, which I will begin to do this afternoon. Now, a remark I wish to share with you. Do not be alarmed by ouch. I have developed an abdominal hernia. Now, this is not serious, not critical, but it sure as hell is painful. And so, as I walk about trying to do my usual animated dance during lecture, because that's the way I operate, I may get a sharp pain right here. That might cause me to sit down. It might be necessary for a class or two to have Andrew Mosen, one of our discussion instructors, step in and present the lecture to you. He's done this for me before. He's quite qualified. There will be no problems. But I will make every effort instead to be with you because I love it, and you know that. But I know I got to get this fixed. The sooner the better. Because as this problem progresses, it gets more painful on a day-by-day basis. And I've been dealing with this now for 3 or 4 months, although I didn't find out what the real problem was until over a week ago. At which time, the physician who saw me referred to a physician who I've seen before to fix hernia. I've not yet been called by that physician's office. So I'm going to take the bull by the horns and call that SOB this afternoon, because I need this damn thing fixed. But as I said, if I go, ow, you know why. Don't worry, I'm not passing away. Even though I might pass out. I don't think that'll happen. But just in case, so that you know. Don't go, oh. Be all right. I meant to post the quiz key to Sockeye the other day. I forgot. I meant to post it yesterday. I forgot again. So I'll try again today. If I have made a promise to you to post a key and I forget, send me an email saying, damn it, post the key. I got a lot of things on my table in regard to the fact that I also run both teaching laboratories for general chemistry, and I'm responsible for interacting on a regular basis with the approximate number of 60 TAs that I have to deal with, about 70% of whom have very limited English communication skills. I'm sure you know about this. In any case, we shall proceed. Indicator gator xanthus, question 1835. This information regarding gator xanthus we recognized last time. This is really given in the statement of the question. Since the boundary pHs are 0.9 and 2.5 respectively, the halfway pH is 1.7, and since the boundary colors are yellow and blue, at the halfway pH we see a distinct green with this indicator because its colorimetric behavior is just like indicators we've discussed previously, in particular HBTB. So, Ka for this indicator corresponds to the hydronium ion concentration at a pH of 1.7. And hydronium ion concentration at a pH of 1.7 is 2 times 10 to minus 2. If you write that as 1 times 10 to the minus 1.7, arithmetically you are right. Chemically you have made a horrible mess of this problem, and I won't accept it. Because if I send you to the laboratory to make me a solution which has got a hydronium ion concentration of 1 times 10 to the minus 1.7, you're going to have a fit. That's why we're not accepting any powers of 10 which are fractional. They all got to be whole numbers. Now then, the question then goes on to say, let's consider a water solution of a methyl acid HQ. Statement number 1, HQ has the same acid strength as HGX. That means KaHQ is the same as HGX. KaHGX. So KaHQ is also 2 times 10 to minus 2. The next piece of information is, when the water solution in question of HQ is treated with this indicator, we observe a distinct yellow-green color. That means a pH of 1.3 and a hydronium ion concentration of 5 times 10 to minus 2. Since for the HQ solution the only solute is HQ, it follows that the hydronium ion molarity and the Q minus molarities are equal. So up top, we got 5 times 10 to the minus 2 quantity squared. And given that the demands of the problem are to calculate m sub I, we have, as usual, x squared over m sub I minus x. That's all it is. So m sub I minus q minus, because q minus molarity is x for this problem. So we got this up top and this down below. Solve it for m sub I, no problem, you get 0.2. Question 1836 says acid HC is twice as strong as HGX, which means HC is also twice as strong as HQ. All that means is that Ka for HC is 2 times Ka for the acids we've just considered. 4 times 10 to the minus 2, no big deal about that. The intention of that question is just to remind you that the measure of acid strength is its Ka value. So if one acid is twice as strong as another acid, that's the same as saying that Ka for the first acid is twice that for the second acid. The stronger acid has got a Ka that's twice that of the weaker acid. So with this we go to buffers. First, a statement. This x squared over m sub I minus x recipe. Recall, that can be used and applies exclusively to a water solution of a single solute ionizing acid or a single solute ionizing base. But how's a buffer prepared? Most commonly, by dissolving in the same solution a high concentration of a given Bronsted-Lowry weak acid, along with, in the same solution, a high concentration of the conjugate base of that weak acid. The example considered in the notes is an acetic acid acetate ion buffer. The example which I'm going to consider is an ammonium ion ammonia buffer. Doesn't make any difference. Each serve the purpose of showing you how the chemistry of a buffer operates. Now then, what's the main purpose of a buffer? It's a pH preserver. Happy human blood, for example, is happy in a pH range of about 7.2 to 7.6. So ideally we could say 7.4. Human blood is a H2CO3 bicarb buffer. We can do some arithmetic on that. Perhaps we will, as our conversations on buffers continue. Other buffer systems in the human body. Tears. Sweat. So if we go back to my day, you would know that the name of the rock group Blood, Sweat, and Tears is also simultaneously naming 3 very important human buffer systems. Now, let's imagine that in regard to our ammonium ion buffer, that this buffer is prepared by mixing 100 milliliters of 1.0 molar ammonium chloride solution with 100 milliliters of 1.0 molar ammonia solution. First recognition, in the resulting buffer, the ammonia and ammonium ion molarities are each 0.50. Do you see that? Don't forget when you put these solutions together, you're diluting the concentrations of the component species in each system, respectively, by a factor of 2. Because when I put the 100 milliliters of this together with the 100 milliliters of this, the ammonia molecules from this system will now be swimming around in a lake that's twice the size. Molarity got cut in half. Same for ammonium ion. Now then, the acetic acid acetate ion buffer discussed in the notes. Is that an acidic, basic, or neutral buffer? How will you determine if a buffer is acidic, basic, or neutral? K values of what? You look at Ka for the acid and compare it to Kb for the base. If Ka is bigger than Kb, acidic buffer. If Kb is bigger than Ka, basic buffer. If you had the unusual system where Ka and Kb were equal, then the buffer would be neutral. I know of no such buffer systems. But I will tell you that on special quiz number 1, which is now finished, maybe I'll release it now, maybe I'll hold it till exam 1 is done. So you just keep your attention focused on exam 1. But I suspect that if you do some practice with this, it'll give you some good exercise in getting ready to be successful with exam 1. So maybe I'll release special quiz 1 this weekend. For the special quizzes, keep in mind, you're at liberty to work together. Use any source of information that you wish, except live professional chemistry help, like me and our discussion TAs. The only kinds of questions we will answer in regard to special quiz questions is to clarify a question if you don't know what the question is asking you. Other than that, it's up to you. Notes, Google, and I'll give you at least 3 weeks. The special quizzes are really special. And they're fun. They're designed on purpose by me to stimulate and inspire very deep massage of what is often referred to as the cranium. One of the questions on this special quiz is, consider ammonium acetate solution. 1 molar. You don't need to hurry up and write this down. It'll be on the special quiz. In 1 molar ammonium acetate solution, you've got 1 molar ammonium ion and 1 molar acetate ion. Ammonium ion is a stronger acid than water. Acetate ion is a stronger base than water. So we have a system which has a high concentration weak acid as well as a high concentration weak base. And the weak acid, ammonium ion, is a stronger acid than water, and the weak base, acetate ion, is a stronger base than water. Is ammonium acetate a buffer system? The answer is no. And it's going to be your job on special quiz number 1 to prove why this is not a buffer system. You don't have to worry about it now. You'll see it. I had fun with one of my faculty friends from Santa Fe who insisted that, yes, this was a perfectly legitimate buffer system. Just like you folks when you're in my office, I said, go to the board. He went to the board and he started writing, and after about 10 minutes his face got quite beet red. Why? Because he realized that he made a mistake. That ammonium acetate solution ain't no buffer. But it does give you a quick and fast solution which gives you a pH of 7.0. Because Ka ammonium ion and Kb acetate ion are numerically equivalent. How about that? But you can think about that further as time passes. Now then, back to this buffer, which is a basic buffer, because Kb ammonia is a lot bigger number than Ka ammonium ion. What is the principal Bronsted-Lowry acid-base equilibrium in this buffer? The principal Bronsted-Lowry acid-base equilibrium in this ammonium ion ammonia buffer. What is it? You know how to play the game. In your mind's eye, you see the PSI for this system, don't you? Implied by that, ammonium ion, ammonia, and of course water and chloride ion. We don't give a damn about the chloride ion because it exerts no effect on pH in water solution. So we look at our PSI, and what do we select from it? The strongest acid. What's the strongest acid? What's strongest base? Products? Ammonium ion and ammonia. But that's the main acid-base equilibrium in this system. And that reaction is ever ongoing in this system. But it leads to no net change in chemistry, and it does not give you a handle on system pH. So given that the most important function of a buffer is to preserve pH, we need to have a way to get a handle on pH for a buffer. This will not provide that handle. What will provide the handle? Ka for ammonium ion or Kb for the base. Either one gives you the handle. Watch out for the ouch. Now to illustrate, which I think is obvious, but we'll illustrate it anyway, how a buffer behaves. For this buffer, if I treat this buffer with a few milliliters of 1.0 molar hydrochloric acid solution, what chemistry occurs? Well, when I add this hydrochloric acid solution, what am I really adding? I'm really adding what? Hydronium ion and chloride ion and water. We don't care about the chloride ion, we don't really care about the water. And when I put the hydronium ion in this buffer system, with what will the hydronium ion react? Extent? Very large. Upshot? I tried to change the pH substantially of this buffer by adding hydronium ion. And the buffer says, you're not going to change my pH much because I'm going to kill the hydronium ion. We added this hydronium ion, the ammonia component of the buffer murdered it and turned it into these products. Did it murder the hydronium ion effectively? You're damn right, the reaction extent is large. Now what if I add the hydroxide ion? Well, now the hydroxide ion gets together with ammonium ion, products ammonia molecule and water respectively, reaction extent large, so I try to change the pH substantially or significantly by adding hydroxide ion. Buffer says, nope, I'm going to kill the hydroxide ion. Now then, for this buffer, we've already noted that to get a handle on pH for this buffer, you could use Ka ammonium ion or Kb ammonia. Either is acceptable. Doesn't make any difference. If you do the arithmetic correctly, you of course must get the same answer regardless of your approach. Now, let's write some general information regarding a buffer. Hypothetical HXX minus buffer. As we've noted, for this buffer, just like we noted with the specific buffer ammonium ion, I can get a handle on pH for this system with HX plus water equilibrium, KaHX, or KBX minus, X minus plus water equilibrium. Because each of these equilibria involves a term which directly corresponds to pH. Hydronium ion, hydroxide ion. As you know by now, if pH is cited for a system, you know its hydronium ion concentration. At least you can do some simple arithmetic to get it, as well as the hydroxide ion concentration. Now, since we're usually interested in pH, I'll use this. The equilibrium which produces hydronium ion, for which K is KaHX. Now then, back to this. Does this apply? No. Why not? Would you believe for a buffer solution that the hydronium ion molarity and the X minus molarities are anything close to each other? Huh? Hell no. Hydronium ion X minus. Which molarity is far greater? Hydronium ion or X minus? X minus is far greater. I started with the system containing a high molarity of X minus. Just like for the ammonium ion buffer. The principal species of consequence from a BLAB standpoint, ammonium ion and ammonia. So in this ammonium ion ammonia buffer, the hydronium ion molarity is a hell of a lot smaller than the ammonia molarity. Just like the hydroxide ion molarity is a hell of a lot smaller than the ammonium ion molarity. So you can't use that recipe when you're dealing with buffers. You can't use that recipe when you're dealing with any chemical system which has two or more solutes which exert a measurable effect on pH. Because then X squared does not hold. Now then, let's do some simple logarithmic arithmetic on this Ka expression. Take log base 10 both sides. I get this. Now let's take this expression and rearrange it ever so simply. Let's put log hydronium ion on this side, which makes minus log hydronium ion, which is pH. And put log Ka on that side, which means minus log Ka. That means pKa. Have you recognized what this small letter p means in pH? What the small letter p means in pKa or pKb? What does it mean? Negative log to the base 10 of. That's what it means. That small letter p means all of that. So, with this logarithmetic, I wind up with this general expression for a buffer in terms of buffer Ka. If I use buffer Kb, then you can work out the arithmetic to see what this thing will look like. Matters not which you use. But since I'm more often interested in pH than pHO, I'll stick with this. This is also commonly known as the so-called Henderson-Hasselbalch relationship. For me, that's the last you'll hear of such. Because I don't give a damn who invented these things or derived them. It really doesn't matter if Shakespeare in fact wrote the Shakespeare plays. What matters is that those plays were written because they're magnificent pieces of English literature. That's what matters. To quote a fellow who I think you've heard of, Albert Einstein, who we are means nothing. Nothing. But what we do means everything. What we do can live forever. But when our days are up, we're gone. Keep that in mind. It's damned important. I really don't like people who spend a great deal of time and effort to see how much light they can get to shine on themselves, to see how big a powerful reputation they can build. What a phony, fraudulent way to live your life. Got no use for that kind of stuff. My main function is to share with you as much knowledge and understanding of chemistry as I can. That's what I'm supposed to do, and that's what I do gladly. That's my contribution. Because as I told you, you're the future. And I want to give you as much benefit, tools, strength as I can so that as you go into the future, you can succeed. How about that? So on we go. And now let's tackle some problems which involve buffer system arithmetic, buffer system analysis. Question 1838 is what we are looking at. That's in the notes. Of course, all these questions, you know, if I put a number to them, that's just a reference to that problem in the notes. Question 1838 is a takeoff on our ammonium ion ammonia buffer. 100 milliliters of 0.80 molar ammonia was put together with 100 milliliters of 1.0 molar ammonium chloride. I'm not writing that down because you got it in the notes. But from that, we can write QPSI. We have for this buffer solution system, 0.080 moles of ammonia and 0.10 moles of ammonium ion respectively. When you're going to do any calculations with any chemical system, as you've already recognized, you've got to have the inventory expressed quantitatively, QPSI. And now we're going to imagine then we have a cylinder with contents HCl gas, and from this cylinder into our buffer system we bubble 0.020 moles of HCl gas. Question: what will be the pH of the buffer after we add the HCl gas? Well, let's start first with determining the pH of the buffer before we add the HCl gas. So before we add the HCl gas, we got 5.6 times 10 to minus 10. Does that number look familiar? What is this number? Ka ammonium ion. Equals the hydronium ion molarity times the ammonia molarity divided by the ammonium ion molarity, where the molarities in question are all equilibrium molarities. Now then, the total volume of this system is 200 milliliters. And rigorously speaking, an equilibrium constant expression, if it's not in terms of partial pressures, is in terms of molar concentrations like this one. To do this arithmetic, do I or do I not need to convert the mole quantities of ammonia and ammonium ion respectively to molarities? Do I or do I not need to convert these mole quantities to molarities? If I'm going to convert them to molarities, I will take 0.080 moles of ammonia and divide it by the solution volume. Correct? In liters. And in the denominator, I'll take 0.10 moles of ammonium ion and divide it by the solution volume. I do not need to convert these mole quantities to molarities. It's unnecessary arithmetic, because I will be dividing a term in the numerator and a term in the denominator by the same value. Why waste my time? Right? That's all that's necessary. These are mole quantities. So what? You want to divide this by 0.20 liters and this by 0.20 liters? What have you achieved? Hey, you always want to keep your wits about you. That's why I try to keep students in touch with the reality of the statement of just getting the answer correct in and of itself doesn't mean a whole lot. Can I paint walls at home with a toothbrush? You're damn right. But I'll tell you what, if you're a painter working for me and you charge by the hour, and I see you painting the walls with a toothbrush, I'm going to ask you to take a drink, a large drink, of concentrated sulfuric acid solution. And I will watch you disappear right before my eyes. And then I'll get another painter. If there's a fly on the wall and you want to get rid of the fly, can you get rid of the fly by shooting at the fly with a bazooka? You're damn right. Of course, you also got rid of the wall. And you probably got rid of your neighbor's house. So keep in mind, just getting the answer is not always indicating that you've done something worthwhile. Just like here. Okay? Now then, in a nutshell, I now know the hydronium ion concentration to be this number times 1 divided by 0.8. So the hydronium ion concentration is a little bit bigger than this number, because I'm divided by 0.8 to get the hydronium ion concentration. That gives me a hydronium ion concentration of about 7 times 10 to the minus 10. Now, let me write down I didn't write it down, but you know what to do. Now let's do this part. Oh, I have it. It is 7 times 10 to the minus 10. I thought I had it written here someplace. On occasion, students have come to me and said, "Can I look at your original notes?" They never make the request more than once. And my original notes are barely intelligible to me. So how they could possibly be intelligible to you is beyond my knowledge. That's why I gave you this nice typed copy of notes. Okay? Here's what we got before we put the HCl in. pH 9.15, hydronium ion molarity 7.0 times 10 to the minus 10. Now then, if our buffer in fact does its thing, when I put in this quantity of HCl, in which direction will the pH change? Up or down? Down. Will it change much? No. Let's take a look. Well, in order to take this look, do you think we might have to pay attention to the chemistry which occurs when we added the HCl gas? Well, what is this chemistry? The HCl gas is bubbled into this buffer. Write the equation for the reaction right now. That occurs when the HCl gas is bubbled into the buffer. To write this equation, with what component of the buffer will the HCl gas react? Ammonia. Extent of this reaction? How large? Does HCl react with water 100% extent? Is this a stronger base than water? So tell me how large? 100%. Bingo. Now then, we're going to do calculations, so we've got to keep a handle on our PSI from a quantitative standpoint. We put in 0.020 moles of HCl gas. How much ammonia did we murder? 0.020 moles of ammonia. I've had students say, well, I kill all the ammonia. Like hell you do. You got 0.080 moles of ammonia. If you think you can go into the jelly bean store, where jelly beans are $2 a pound, and buy all the jelly beans the guy has when all you got in your pocket's $1, you're wrong. If I want to kill all the ammonia in here, I got to put in at least 0.080 moles of HCl. All right? So, by this transformation, I will produce 0.020 moles of ammonium ion as well as 0.020 moles of chloride ion, with which I have no concern because of the no impact on pH by chloride ion. And I will murder 0.020 moles of this, which means after I do this murdering, how much ammonia is left? 0. So, here's what I now have. Again, I don't need to divide these by system volumes. Who cares? Unnecessary arithmetic. So 0.060 for ammonia up top, 0.12 for ammonium ion down below. This is how the system inventories quantitatively for mole content after I added the HCl gas. And this is really tough arithmetic here. So the hydronium ion molarity is now double this. And that gives you a pH equal 8.95. Didn't change much, did we? pH came down, but not a whole lot. Now, one remaining question for today. Water by itself, ever so obviously, contains a high concentration of a weak acid as well as a high concentration of a weak base, namely water. Is water a buffer? Our system volume here was 200 milliliters. Tell me, given that the pH of our water is 7.00 to 2 sig figs, if I added the 0.020 moles of HCl gas to my 200 milliliters but now of deionized water, what hydronium ion concentration would I get? .020 moles of HCl added into 200 milliliters of water. What hydronium ion molarity do I get? 0.10 and a pH of 1.00. I changed the pH of the water from 7.00 to 1.00. Is water a buffer? Hell no. Just like ammonium acetate. Keep that in mind because that's the one you'll deal with on special quiz number 1, as well as a bunch of other stuff.